Welcome back, folks. This is Jack with the third and last presentation on shift registers. Now, we ended the previous presentation, part 2, looking at applications of shift right and shift left for numerical manipulation. Now we go ahead and look at some other configurations of shift registers and applications of shift registers. Right. Now, all these different configurations are only different in the way the inputs are applied and the outputs are kind of retrieved from the registers, shift registers. Now, the first one is serial in, serial out shift register, SISO register, and what this is the data is loaded in one bit at a time, serially, and the data is retrieved as well one bit at a time. Now, you can see the flip-flops there. Q's are connected to D's. Clock is a synchronous connection. It's a negative edge triggered flip-flop. We have a clear line here as well. I've not kind of shown the load line here. I did show it on the kind of block diagram, but not internally. But there should be a load as well there, for the reasons I explained in part 1. Now, let's have a look. Now, the way data is actually passed on this shift register is as follows. Initially, I hope you can all see on the bottom left of the screen I've got some tables there of results. Now, if we look at the first row, that's clearing all flip-flops, flip-flop A, flip-flop B, flip-flop C, flip-flop D. Clear them, so outputs are 0, 0, 0. Now, there is only one output from this shift register. That's the out. This is the flip-flop on the extreme right, and that's the output there. Now, clear all the flip-flops, so the results of Q1, Q2, Q3, Q4, all Q's are 0. Then, on the negative edge of the flip-flop, of the negative edge of the clock, place data in so it's shifted into the flip-flop. Now, can you see on the first negative edge I've got 1, 0, 0, 0. Second negative edge I've got 0, 1, 0, 0. Third negative edge I've got 1, 0, 1, 0. And the fourth negative edge I've got 0, 1, 0, 1. So every negative edge I'm placing more data and it's getting shifted into the flip-flops. On the fourth negative edge I've successfully loaded my values into the flip-flops. Right, once all the values have been loaded in the flip-flops, then what we can do is push more values into the flip-flop from the input and kind of retrieve them as they come out of the flip-flop. So put a 0 in, that'll knock the 1 out that was on flip-flop D. Put another 0 in, that'll knock the 0, 1 out. Another negative edge, that'll knock the 1, 0, 1 out. Another negative edge, that'll knock out 0, 1, 0, 1. So data is loaded serially and retrieved serially as well. So you need about 8 clock pulses to load and retrieve the data. This is a serial in, serial out shift register. You may think, what's the application of this shift register? Well, this particular one, I would say a time delay. We can actually delay by 8 clock pulses the data going in and coming out of the shift register itself. Okay, that's the first configuration. The second one is serial in, parallel out. SIPO shift register. Serial in, parallel out. Same way, the data is loaded serially one bit at a time. So exactly the same as before, but this time the data is not retrieved serially, it's retrieved in a parallel basis where we've got Q1, Q2, Q3, Q4. So after 4 successful clock pulses, all data is present on Q1, Q2, Q3, Q4, serial in, parallel out. What's the application of this particular shift register? Well, on this particular one, it's used for serial to parallel interfacing. One particular example could be on the output of a microcontroller. You might have a serial in, parallel out shift register, and this allows you to connect many peripherals to the output of the shift register. There may not be that many port pins available on the microcontroller, so it allows you to kind of expand the I/O using shift registers. Parallel in, serial out is the opposite of the previous one. We're going to load data in at once, however we're going to retrieve the data one bit at a time at the output of the flip-flop to the extreme right of the picture, which is flip-flop D. Now the way I've shown it here, it's shown differently in certain circuits. They might show as a combinational logic circuit, but you need some other form of logic to load the data in a parallel form. I've used a 2-to-1 multiplexer, which has one control line, which is load or shift. It's either loading the data or shifting the data. Once the data is loaded, then we can successfully shift it along. So remember, load and shift in reality for this is just a select line, which controls whether the parallel input is connected to the D or whether Q is connected to D. So in order to load the data, the parallel A, parallel B, parallel C, D. So in order to load the parallel data, I'll call it parallel A, parallel B, parallel C, parallel D bits, we initiate the load, make the load active, which either may be 1 or 0. I've not kind of specified that at all, but all that happens is the D's are connected then to the parallel bits. Once data has been loaded into the flip-flops, then we can actually shift the data by making a shift active, and all that does is connects the Q to the D's. So once parallel data is loaded, then just shift it along, in this case shifting to the right. And what happens, first we can clear it, which makes it 0, 0, 0. Parallel load the data. For example, I've done 1, 0, 1, 0 for flip-flop A, flip-flop B, flip-flop C, flip-flop D. So we've got 1, 0, 1, 0 loaded into flip-flops. Once that occurs, simply shift it. There should be a negative edge clock as well every time, but I've not kind of shown it there. So shift, 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 shift allows one bit of output to occur every time. And after 4 successful shifts, 4 successful clock pulses, negative edge triggered clock pulses, all the data is present. Now, what's an application of this? An application of this is parallel to serial interfacing. This could be at the input of a microcontroller where you've got many peripherals connected to the input of it, but output of it is just one bit, which can go into a microcontroller. So it kind of allows you to be very kind of efficient in using the microcontroller pins. This is just one example. Usual PISO and SIPO registers are used for interfacing, where parallel serial conversion is required. For example, a modem is another example of what's required. Okay, now parallel in, parallel out registers, PIPO, now these are technically called shift registers. I don't see where the shifting is occurring in this particular register. It should really just be called a register. However, it still is called a shift register, and the only application of this I can think of is just storing memory and retrieving memory. Just as the same example as I gave before with a block diagram, this is just a simple register which allows us to store bits and retrieve the bits when we want them as well. Right, so that's that. Okay. Now, shift register applications. Shift register applications include parallel serial interfacing, multiplication and division, and also time delay. So, just to recap, serial in, serial out can be used for time delay applications. PISO, parallel in, serial out, can be used at the input of a microcontroller to reduce the amount of input pins required. SIPO, serial in, parallel out, can be used at the output of a microcontroller to reduce the amount of output pins used. PIPO, parallel in, parallel out, is not really a register. There's no shifting occurring there. It's just a simple memory device, really, just like a register that we looked at before. Okay, by no means this is an exhaustive list of applications of shift registers.